So the title of the paper I'm presenting is FPGA based on integration of CMOS and RRAM. This paper introduces a novel CMOS nano hybrid reconfigurable field programmable gate array utilizing resistive memory devices. The reconfigurable FPGA or RFPGA primarily comprises 1T1R RRAM structures achievable through a CMOS-compatible process, enabling efficient FPGA block memories. Notably, the paper presents novel RRAM routing switches as replacements for CMOS routing switches to achieve significant density enhancement and power reduction. Simulation results illustrate that 2D and 3D RFPGAs offer a 2 to 3 times improvement in area with 20% lower power consumption compared to corresponding CMOS FPGAs. The results highlight the potential for improved performance and efficiency in reconfigurable computing systems. The introduction of the paper discusses the use of FPGA chips in electronic system design, particularly for prototype development. The properties of FPGAs, such as reconfiguration and defect tolerance, are seen as attractive, especially as CMOS technology scales down to nanometer ranges and the fabrication yield of IC components does not often approach 100%. The paper highlights the significance of the routing resources in FPGAs, accounting for more than 70% of the total area, delay, and power. Also mentioned is the potential of bistable junction nanodevices for building memory and routing elements in FPGAs. In the remaining sections of the paper, first, 1T1R-based RRAM devices are introduced as block memory for the RFPGA. Then 2 novel RRAM routing switches are discussed as the FPGA's routing resources. The paper then discusses the 2D and 3D RFPGA architectures and presents the circuit designs of block memory, connection block, and switch block. Then the paper also examines the fabrication and integration procedures of 2D and 3D RFPGAs and provides the results of the performance evaluation and benchmark circuit simulation. The second section of the paper is dedicated to resistive RAM as memory element and routing switch. The resistive RAM has high density, low voltage, and low power properties that make it an attractive candidate for replacing traditional memory solutions. It offers advantages over flash memory, such as lower programming voltages and fabrication compatibility with CMOS, and addresses the issues of high electric field and disturbance during program erase operations. Comparing to flash memory, RRAM has the potential for scaling down to several nanometers, making it a promising option for future memory technologies. And compared to SRAM, RRAM offers similar programming voltage and operation speed, with higher density and better scaling possibilities. In this section, 1T1R structures are used to obtain NOR and NAND RRAM cells, with the demonstration that the NOR RRAM cell is superior to the NAND cell in terms of speed and density. The NOR RRAM cell is also suggested as a replacement for the SRAM block memory, as it requires only 1 transistor, leading to a significant reduction in size compared to the 6-transistor SRAM cell. There is also the added benefit of reduced standby power due to the resistance-based information storage of the RRAM. The next subsection discusses the integration of nanojunction devices with CMOS devices to create 2 new routing switches, 2T1R and 2T2R, aimed at improving the performance of the 7T SRAM routing switch. The 2T1R structure includes 2 programming transistors used to configure 1 junction during the configuration stage, while the 2T2R structure uses 1 programming transistor with a programming voltage to configure 2 complementary junctions. These new switches offer significant enhancements in device density and reduced standby power consumption compared to the 7T SRAM routing switch due to the use of nanojunctions. The standby power of the proposed switches is around 1/3 of the power consumed by a 7T SRAM routing switch, leading to substantial power savings. Then, in the delay analysis, the paper indicates that the 2T1R switch is expected to operate faster than a 7T SRAM switch or a 2T2R switch. However, the 2T2R switch might still be more promising for FPGA applications, due to the separate programming circuit and signal transmission, ensuring reliable circuit operation. In the next section, circuits and architectures of 2D and 3D reconfigurable FPGAs are built from RRAM memory cells thanks to their high density and low power consumption. The proposed 2D reconfigurable FPGA integrates RRAM devices to build FPGA building blocks, maintaining the baseline 2D FPGA architecture. The block memory is based on NOR RRAM cells, while the switch blocks and connection blocks utilize 2T1R and 2T2R routing switches. The NOR RRAM block memory uses a CMOS current-based I/O circuit, which differs from the voltage-based I/O circuit of the SRAM block memory in the baseline FPGA. The use of 2T1R RRAM switches in connection blocks results in a high-density and low-power design, with a significant area reduction and delay reduction compared to the traditional SRAM CMOS connection block. The use of 2T2R RRAM switch for connection blocks also offers similar standby power savings. The proposed 2D architecture also integrates RRAM switches into the switch blocks for global routing. The RRAM switch block designs demonstrate complexity reduction and delay improvements compared to CMOS-based switch block designs. The 2T1R-based RRAM switch block designs show significant delay reduction and standby power saving, while the 2T2R-based RRAM switch block designs maintain the same delay values as the 7T SRAM switch-based designs. In the next section, the 3D reconfigurable FPGA is proposed. The 3D architecture is designed as a face-to-face two-layer structure with bumps serving as bonding elements and communication channels between the layers. The bottom layer contains CMOS logic blocks and RRAM block memories, while the top layer contains RRAM-based switch blocks, connection blocks, and block memories. Each logic block in the bottom layer is linked with 4 connection blocks of the top layer using bumps. The block memories in both layers are NOR RRAM circuits, and together with the connection blocks and switch blocks, they provide high density, efficiency, and low power consumption. According to the paper, the 3D architecture is expected to reduce the interconnect area, delay, and power of the 2D FPGA by 20 to 40% due to the significant reduction in interconnects. Additionally, the use of RRAM memory and routing switches will further improve the 3D CMOS FPGA in terms of area and power. Also, the paper acknowledges the challenge of thermal management in 3D ICs, but suggests that replacing CMOS devices with non-volatile RRAM devices can lead to a significant reduction in power. The next section of this paper discusses the fabrication and integration of 2D and 3D reconfigurable FPGA architectures. The 2D RFPGA architecture allows for an efficient CMOS-compatible fabrication process involving additional steps such as deposition, etching, and chemical-mechanical planarization to build the vias with nanojunctions. On the other hand, the fabrication of the 3D RFPGA requires a face-to-face 3D integration process where 2 separate CMOS RRAM dies with the interconnect layer are fabricated and then thinned and bonded together in a face-to-face manner. In the packaging process, the 3D RFPGA's I/O blocks needs to connect to the substrate. And for this I/O bonding, the wire bonding method is the standard approach. The paper indicates that the 3D integration method focuses on the bump and wire bonding method, as the proposed 2-layer face-to-face architecture can take advantage of these existing bonding approaches. However, if the 3D architecture consists of more than 2 layers, then the through-silicon via method might be considered, although it is more challenging than the bump and wire bonding methods. The paper also predicts some of the challenges of the 3D RFPGA fabrication and integration, such as the preparation of bumps for signals and power delivery. In the next section, the paper presents a detailed performance evaluation and comparison by first estimating the performance of the 2D and 3D RFPGA chips, and then simulating them in benchmarks and comparing with the corresponding CMOS FPGAs. In the performance analysis, features such as density, critical path delay, and power consumption are considered. In the comparison of complexity between SRAM and RRAM block memories, the results show that 2D RFPGAs using RRAM devices can achieve significant density improvements over baseline 2D FPGAs. Similar results can be observed comparing 3D RFPGAs to its CMOS FPGA counterpart. For critical path delay, improvement is expected only when 2T1R routing switches are used for the connection blocks and switch blocks. This expectation holds for both 2D and 3D architectures. In the part about power consumption, the distinction is made between dynamic and standby power. The paper states that while dynamic power can be estimated through simulations, the standby power consumption is also considerably large. The use of 2T1R or 2T2R routing switches is expected to significantly impact standby power, and the use of NOR RRAM is also capable of large standby power improvement. The analysis also indicates that the 3D architecture is not expected to deliver major effects on standby power, and it is likely to perform similarly as the 2D RFPGA. The next section presents an evaluation of benchmark simulations for 2D and 3D RFPGAs compared to traditional CMOS FPGAs. The simulation is carried out using Toronto 20 FPGA benchmark circuits for both 2D and 3D architectures. Since the RFPGA maintains the CMOS FPGA architecture, its design and simulation can therefore utilize CMOS FPGA CAD tools such as VPR. The inclusion of RRAM devices in VPR involves generating models of junction nanodevices using Verilog A and incorporating them into the VPR CAD flow. The results show that the 2D RFPGA provides a 2 to 3 times improvement over the 2D CMOS FPGAs in terms of area, where the 3D RFPGA's improvement over the 3D CMOS FPGA is less than 2 times. In terms of delay improvement, the 2T1R based RFPGA is approximately 10% over the CMOS FPGA, while the 2T2R based RFPGA exhibits similar delay performance to the CMOS FPGA. Additionally, both 2T1R and 2T2R based RFPGAs demonstrate a total power improvement of around 20% for both 2D and 3D cases. It is noted that the use of 2T1R or 2T2R routing switches produces a significant improvement for standby power, but a modest improvement for dynamic power consumption. This section concludes with the statement that compared with high-end FPGA with block memory and logic circuits, the 2D and 3D RFPGAs are expected to provide at least 2 to 3 times area improvement with 20% lower power. The 2T1R RFPGAs also achieves 10% higher speed than the CMOS FPGAs. In conclusion, the paper introduces a new CMOS nano hybrid FPGA platform called RFPGA, which incorporates resistive RAM devices in the memory and routing designs of the current FPGA framework. This approach allows for the continued use of current FPGA architecture and software, providing an efficient near-term solution for FPGA industries to leverage RRAM emerging devices. The RFPGA exhibits several key properties. Firstly, the 1T1R-like RRAM devices are CMOS compatible and seamlessly integrate with CMOS circuits. Secondly, the novel 2T1R and 2T2R routing switches significantly reduce the complexity of FPGA routing resources, resulting in a 2 to 3 times density increase and 20% power improvement for the logic part. Additionally, RRAM-based block memories offer a 6% area and power reduction compared to SRAM block memories. Furthermore, RFPGAs maintain existing designs and can utilize the current CAD tools of CMOS FPGAs. Moreover, through the use of the face-to-face 3D integration method, a 2D RFPGA can be expanded to 3D, offering further density, speed, and power enhancements. The paper emphasizes that due to these superior properties, RFPGAs are anticipated to drive innovation and technological breakthroughs in establishing reconfigurable ICs for future nanotechnology.